Hey everybody, welcome back. We've got a Calc 2 style integral where we want to use partial fraction decomposition. So the first thing that I want to do is I want to sort of put the calculus on hold and I want to deal with the algebra. I want to break this up into the sum of fractions. And so my goal is to use the partial fraction decomposition technique. Okay, so as I mentioned before, let's put the calculus on hold and deal with the algebra. So after we write this, the next thing we want to do is classify the factors in the denominator. So this factor is linear and unique. This factor is quadratic and unique, and it won't factor further using real factors. So for a linear unique factor, we need a constant a over that factor. For quadratic unique, we need bx plus c over that factor. Our next goal is to find a, b, and c. And so really that's more algebra. So we want to get rid of the fraction. So what we want to do is multiply the whole thing by this, which is the least common multiple of all the denominators. So multiply everything by x plus 4 times x squared plus 9. Okay, so I'm going to distribute. And as I distribute, I'm canceling, right? So I'm distributing this here. Notice this would cancel with this. I distribute this here. Notice the x plus 4s would cancel. And then I distribute this here. Notice the x squared plus 9s will cancel. Okay, so the next thing we want to note is this equation is true for any x. So what we want to do is pick convenient x's that will allow us to find as many of these a, b, and c as possible. Well, notice if x is minus 4, this will drop out and I can solve for a. Okay, so if x is equal to minus 4, I can plug that in for all x's. So on the left, we get 16 minus 36 minus 5 is equal to 16 plus 9a. Okay, so that's minus 25 equals 25a. And so right now we have a. A must be minus 1. Okay, notice that for a real input, this won't vanish, right? And that's a problem because I want to find b and I want to find c. So it seems as if I'm stuck, but at this point I want to do some algebra. So when I'm stuck, I want to multiply everything out with the goal of equating coefficients. All right, so what do we have here? So a x squared plus 9a plus, looks like bx squared plus 4bx plus cx plus 4c. And I'm going to double check. I think that's a good idea because one mistake here could potentially ruin the problem. So it's always smart to double check. Okay, so I'm happy about that. So now we want to organize these. So I like to put symbols down to help me organize. So for my squares, I'm going to write a square. For my linear terms, a little line segment. And for my constants, maybe a smiley face. So now I'm going to rewrite these. Again, my goal is to equate coefficients. Okay, so the square terms will go together, and I can factor out an x squared to the right. You see how we did that? We collected these, and we right factored x squared. So now let's collect the linear terms and right factor the x. So that's going to give me 4b plus c times x. And then lastly, my two constants will go together. Again, I'm going to double check. Okay, seems good. Now the idea here is if these are equal polynomials, the only way that they're equal is if their coefficients are equal. That means that the coefficient of x squared on the right must equal the coefficient of x squared on the left. And the coefficient of x on the right must equal the coefficient of x on the left. And this group of constants must equal this constant. So that's what I mean by equating coefficients. But notice, we already know that a is minus 1. So let's just take note of that. A is minus 1. And if a is minus 1, that forces b to be 2, so that the sum is 1. So now I can use either of these equations to find c. Let's use this one. So 4 times b, that's going to give me 8, plus c is 9. C must be 1. And so now I know a, b, and c. So what does that mean for us? It means essentially this integral is equal to this integral. So let's actually write that. And so the original integral, which was too complicated as given, is equal to this nicer form. But we're pretty happy because we know what a, b, and c are. And so it looks like we're really trying to solve, well, a we said was minus 1, right? So we need a over x plus 4 plus, now b we said was 2, so that's going to be 2x. So bx, 2x, and c we said was 1. So it turns out that this will be much easier than this. So partial fraction decomposition, super powerful. You'll see it again in differential equations. And again in the future, if you take complex analysis. Well, as this stands, it's not quite a u sub because of the plus 1. I mean, if this was u, its derivative would take care of this, but that plus 1 is problematic. So break this fraction up. Of course, in this c is not 0. But we're going to use this technique to break this up. So this is like my a here. X squared plus 9, that's like the c here. And this is like the b, the plus 1. So it's just like common denominators in reverse. Instead of putting fractions together, you're sort of, in some sense, ripping them apart. And I'm going to split this into 3 integrals because they require different techniques. I know the first and the third they're sort of instant, but I want to show my work. So remember, the integral is additive, so I can break it up over a sum. And specifically for this one, I'm going to end up using the following substitution. Now, some people might instantly see this, but I like to show my work in detail. I always assume my work is for an audience, so I like to be as clear and detailed as possible. Okay, so what do we really have? Looks like this. Okay, that's not so bad. So this right here, this is a natural log. So this is going to be the negative ln of absolute x plus 4. Maybe I'll say plus c1, one constant of integration. So this right here is the natural log of absolute u plus some c2. And then here, this is in an arctangent form. So this will be, remember, if this is a squared, I need 1 over a arctan of x over a plus a third constant of integration. But now we can just write this as a single integral and then add the constants for one single constant. Now remember, x squared plus 9 is positive for every real number x, so I don't need an absolute value here. And I'm just going to note where c is equal to c1 plus c2 plus c3. Okay, and so there is an example using partial fraction decomposition. Super powerful tool.